In this session, we explain the instruction and data flow in Intel 8086 and the arrangements of even and odd memory banks. As far as the instruction and data flow in 8086 is concerned, we have seen that in 8086 there are separate blocks for storing separate segments for storing program and data in memory. In this, as per this storage differences, the program area has been accessed by the code segment register, and data area is accessed by data segment register, extended segment register, and stack segment registers. So with the help of these registers, different segments can be accessed directly, and the program and data can be made available for the processor for arithmetic and logic operations. What are the different steps in program execution? Will be seen over here. Program instructions stored in program memory can be accessed through the data lines by placing the address on the address bus. Base address of the first instruction will be taken from the code segment register. So base address first instruction of the base address of the program is already stored in the code segment register, and the offset address is stored in the current instruction. The offset address of the current instruction or the first instruction in the program is already loaded in IP register, instruction pointer register. So how the 20-bit address is being calculated is our primary concern. So 20-bit address is calculated as like the content of the code segment register is been moved 4-bit logically left. So that is been done by multiplying the code segment register by a value 16 to the base 10. So why this is been moved? It must be logically shift left for adding the IP register content. So IP register now has the offset address of the first instruction of the program. So this is been added with the content of register shifted 4-bit left. Now this address, this 20-bit address thus generated is placed on the address line, and the read signal is made low. Now along with that, the IP register content is being incremented by 2, because next cycle the instruction pointer must be pointing towards the next instruction to be executed. So from the current instruction it is being moved to the next instruction. So since the word length is 2, it must be increased by 2 for pointing to the beginning of the next instruction in the memory. Now after that, one word of program is placed on data bus, and the RD is made, read signal is made high, data bus content placed in 2 empty locations on instruction queue. As we have seen in the internal architecture of 8086, there is an instruction queue in the execution unit, and the instruction is placed in the and the instructions are placed one by one in the FIFO manner to be taken by the execution unit. So the currently accessed data is now inserted into the instruction queue, into the free locations, 2 empty locations. The data is placed. Now these steps will be repeated until an instruction, a branching instruction is been executed. So these are the steps for continuously for the instruction to be taken into the processor. An instruction execution unit reads this first instruction from the queue, that is in the first in first out manner. The first 2 consecutive location instruction has been read by the execution unit. Then this instruction is decoded and it is being executed by the ALU, arithmetic logic unit. if the instruction needs data, either the instruction wants to read some data, the instruction is operating on some input data, or it gives us result as as data, then in both the cases the bus interface unit interrupted to read write in this particular data. So now the bus interrupt unit is actually going on with fetching instruction and adding to the instruction queue. Now it will be stopped that operation and now ready for either data input or output. This will be done after it completing the current fetching of instruction. Then 20-bit data memory address is generated, and accordingly either the data is fetched from the memory or data is placed into the memory. Now even and odd memory banks. So as we know, the address is of length 20 bit in 8086 and each data is of length 8 bit, means 1 byte of data. So if you calculate the total memory, you can say 2 raised to 20 locations are there. That means 1 MB of memory space available for direct accessing. Now one location stores 8 bit. So one memory location is needed for storing 1 byte of data. So if you take the 2 consecutive locations, then 16 bits can be stored in 2 consecutive locations, or we can say 1 word is stored in 2 consecutive locations. 1 MB, one memory, the space of 1 MB is being divided into 2 banks, even and odd memory banks in 8086. So 1024 KB is now being divided into 512 plus 512 2 banks, 512 KB plus 512 KB. Now the even or lower bank, one is even or lower bank, 1 unit of memory is that is 512 KB is even bank, or we call it as lower bank, and the other 512 KB is called the odd or upper bank. So these even bank and upper bank are represented as 2 memory IC chips. Data, as we know, the data, there are 16 lines for representing the data lines. D0 to D7 connected to the even bank, and D8 to D15 data lines are connected to the odd bank. Even bank is selected if the signal A0 is high, and odd bank is selected for reading or writing data if the bus high enable signal BHE is asserted. So the even bank is selected by A0 signal and odd bank is selected by BHE signal. Memory location is selected by the address lines A1 to A19. As we know, the address lines, there are 20 address lines starting from A0 to A19, and the first address line A0 is used as a signal line for selecting the even bank, and remaining remaining lines, the address lines starting from A1 to A19 are used for transferring the address. So particular memory location is selected by placing the address on the address line starting from A1 to A19. Now, in the case of memory access from memory banks, how the data is accessed, how the locations are accessed when the memory is being divided into 2 banks, upper and lower, or odd and even. There are different cases of accessing memory, as we can see over here. First case says that when a byte is accessed from the even bank, what are the steps that will be performed when 1 byte of data is accessed from the even bank? Now, In this case, as we seen in the previous slide, A0 is made low and BHE is made high, because the signal A0 is for selecting the odd bank and BHE is selected for selecting the even bank. So here A0 is made low and BHE is made high. Then the data transfer is done through the lines D0 to D7. As we know, D0 to D7 are connected to even bank. Now, the second case, consider the second case where where the processor is accessing 1 byte of data from the odd bank. Here, A0 is the signal A0 is asserted high and BHE is made low. Then the data transfer is done through the lines D8 to D15, and these lines are connected to the odd bank. So data lines D0 to D7 are connected to the even bank and D8 to D15 are connected to the odd bank. Now the word access from even boundary. So these two cases, first two cases are for reading 1 byte of data, means 8 bits of data. Now the second case is reading one word. One word is actually 2 consecutive locations, that means 16 bits. So one word is 16 bits, means 2 bytes. Now if you want to read 16 bit of data, that is one word, then the low byte is in the even bank and the consecutive high byte is in the odd bank. So we have to read 1 byte from the even bank and another byte from the odd bank. So for this we select A0 and BHE, both are made low, means both the banks are selected. So in this case, we have selected the even bank. So A0 is made low, BHE is high. Now in the second case, A0 is high and BHE is low. So in both the cases, we need only one bank at a time. But here we need both the banks. So both A0 and BHE are made low. So the data transfer is done through D0 to D15. That is D0 to D15. The data lines D0 to D7 are taken from the even bank and D8 to D15 data lines are connected to the odd bank and data is taken from the odd bank. So here the word is accessed from the even boundary. Now look at the last case. Here the case number 4. Here the word access from odd boundary, starts from odd boundary. So this cannot be done in one bus cycle. Here it must be done in 2 different bus cycles. So that must be very careful. 2 different bus cycles are needed in the case of word access from odd boundary. Now the low byte is in odd and next address is even. So the low byte is stored in the odd bank and higher byte is stored in the even bank. In the previous example, it was low byte is in even and the next data is in the odd bank. So here we need the low byte first. So the data must be taken from the odd bank now. For that, in the first cycle, the odd bank is selected and data is transferred. In the second case, the next bank is selected and the data is placed on the other set of lines, data lines. So here we need 2 consecutive bus cycles for reading the one word of data from 2 different banks. Here is the internal structure of the organization of even and odd memory banks. As we can see, this is the address space, total address space 1 MB to 1 MB is represented as 00002 FFFFF, and that is been divided into 512 KB each. So this is odd memory and this is even memory block. and or the addresses stored here can be explained as like the odd addresses 000 are stored in odd bank, and the next data 0001 address is in the even bank and odd bank. So odd address 0001 is in odd memory, and the even address, corresponding even address, next even address is in the even bank. So here, this is how the memory is being organized. Now the odd memory is connected to the lines, connected by the data lines D8 to D15, whereas the data lines D0 to D7 are connected directly to the even memory bank. So the data lines are being splitted, and each set of lines are connected to each memory bank. And BHE signal is used for selecting odd bank, and A0 signal is used for selecting even bank. So the address latches are used over here for transferring the address lines, and CPU bus is needed for database transfer. So this is the internal configuration of even and odd data banks in 8086 processor. Now this is the status of the signals used for selecting the different banks, odd and even, during memory access. A0 and BHE. Can see the different configuration when A0 is low and BHE is high, when A0 is high and BHE is 1, when both are asserted 0, and when we want 2 bus cycles for access. In the first bus cycle, A0 is made high, BHE is made low. In the second bus cycle, A0 is made 0 and BHE is made 1. So accordingly, the different data lines are selected. And in first 3 cases only single bus cycle is needed, but in the last case 2 bus cycles are needed. Now why we need memory banking is the primary question. The 8086 processor provides a 16-bit data bus, as we know, and it is capable of transferring 16 bits in one bus cycle. But each memory location is only is capable of storing 1 byte, means 8 bit of data. So if you want to read a word, that means 2 bytes, then 2 cycles are needed. So in one cycle 8 bits will be read, and in the second cycle another 8 bits. So 16 bits will be read in 2 bus cycles. So in order to avoid this, we go for something called memory banking. Through memory banking, the access is allowed at consecutive memory locations in one cycle itself. That is, we can transfer 16 bit of data in a single cycle by consecutively taking 8 bit from one bank and another 8 bit from another bank on the same single bus cycle itself. Memory chip is actually equally divided into 2 halves, first half and second half, first part and second part, even and odd bank. One of the banks contain even addresses only, and it is called even bank. And the other block contains only odd addresses, and we call it as odd bank. Even bank always gives the lower bytes, so even bank is also called a lower bank. Similarly, odd bank also is called a higher bank because it's always represent the higher byte of data of each word. Now, it allows the memory banking configuration allows to access 2 aligned memory locations from both the banks simultaneously and process 16-bit data transfer in a single bus cycle. So it doesn't, one thing we have to notice is that doesn't make it compulsory to transfer 16 bits. It facilitates the 16-bit data transfer. So it's, we need not go for a 16-bit always. We can either go for 8-bit transfer also by selecting one of the banks. But in one cycle itself, we can transfer 16-bit of data. The choice between 8-bit and 16-bit transfer depends on the instructions given by the program. In the instruction set itself, we use either byte data or word data. Depending upon that, either one of the bank is selected, accessed, or both the banks would be simultaneously accessed. So this is the necessity of data.